We're going to fast forward now to the middle of the 20th century, where, as we have noted several times before, there was a major intellectual change with the advent of a variety of innovations, including the development of the computer metaphor, the development of information theory, and shortly thereafter, of course, the development of cognitive psychology and generative linguistics. But right around this time, in the 1940s, in fact, an equivalence was drawn between the terms of this new language of computation, logical circuits, and so on, and nervous systems. And it was mainly to be attributed to Warren McCullough, the guy in the top left, who usually published with Walter Pitts on the right. In fact, they had a very, very long history together, very interesting history together. And perhaps the key paper here comes from 1943. It was called A Logical Calculus of the Ideas Immanent in Nervous Activity. That's quite some title, and here it is. There's that 1943 paper, often cited, rarely read. And the argument in this paper lays the foundation for thinking of what neurons are doing as if they were computational elements that were taking inputs, transforming them in a regular fashion, and producing outputs in a fashion that could be captured by logic, that is, the mathematics of simple states, ones or zeros, true or false. Let's just have a quick look at the abstract of this paper. Because of the all or none character of nervous activity. The all or none character of nervous activity here refers to those spikes. So we've already seen that McCullough has selected these spikes as the crucial goings on in the nervous system that he's going to build his theory around. He says neural events and the relations among them can be treated by means of propositional logic. So here's the leap from spikes in tissue to the terms of mathematics and logic, propositional logic. And there's a great deal of discussion then about the manner in which neurons are linked and how that will affect the transformations that they effect on inputs as they produce outputs. So here's some of the diagrams from that paper. And these represent little, you can think of them as little logical circuits. In fact, they are little logical circuits. The graphical elements employed are somewhat non-standard, but these are simplified, abstract notions of a very simple idea of what a neuron is, connected together in parallel and in series in order to compute certain functions. And when you do this, when you adopt this view of the nervous system, then there's an awful lot of analysis to be done, mathematical analysis. McCullough and Pitts distinguish between two kinds of connections within a network. And they're all based on an abstraction taken from the neuron as if the spike were the only element that we need consider. These are hugely simplifying assumptions, but it turns out that when you build a network inspired by this vision, and you can do this mathematically, you can write programs in which there are simple computing elements that sum their inputs and generate outputs. We call those artificial neural networks today. Then there's two basic distinctions. Networks without circles, as shown here, corresponds to chains of processing, such that inputs are transferred along a stream, ultimately producing outputs. Those in the language of artificial neural networks are known as feed-forward nets. Nets with circles are quite different. Once we have neurons connecting to neurons connecting to neurons, which ultimately connect back to the original neurons, entirely different mathematical properties jump out. These, in the language of artificial neural networks, are known as recurrent neural networks. And in the spring, I'll be teaching a course on connectionism and dynamical systems, where this distinction will play a big role. So McCullough here has hugely changed the game. He has produced an abstract mathematical view of what a neuron is. He's employed the language of the time, the emerging vocabulary of the computer and information system. And this set the scene then for a vast body of work, which persists to this day. He founded the entire field of artificial neural network research, for example. Very, very influential work. And as you can see, this twist that happened in the middle of the 20th century with the coincidence of information theory, the idea of the von Neumann computer architecture, then McCullough's brave leap, trying to interpret brains in that fashion. Then after that, the enterprise of generative linguistics. We've got the stage for what we'll call the era of cognitivism, which is the second half of the 20th century. And at the heart of this is the abstract view of the neuron taken by McCullough and Pitts. It's a mathematical abstraction, and we have little, I wouldn't like to assert that McCullough had found out how a neuron works, nor I think would McCullough have asserted anything like that. Rather, he presented a formalism within which formal mathematical theories could be employed to address many of the questions that arise as we approach brains. So this is a very powerful mixture that will give rise to computational theory of mind and cognitivism.